Vincent Beffara from so Lyon, Bonn, and soon Grenoble for the last talk of this wonderful conference, and you will talk about
random walks.
Good job.
So thanks, and it's not a very easy task to be the last speaker, so I will do as if I was not the last speaker, and then at the end of the talk I will well, do my job as the last speaker. So I wanted to find a topic that was something I had done or was doing, and that was related to work of Greg, and that was not about SLE. And I did find something, and the drawback of choosing this particular topic is that it's completely unfinished, and some of it is a little bit speculative, and I still think there are some interesting ideas in it, but don't trust me 100% on what I will claim. Some of it might be wrong, but hopefully the main ideas will be still relevant. So first of all, this is partially joint work with Vladas Sidoravicius. And essentially I want to describe to you two models related to random walks. One of them which is interesting and completely obscure and untractable, and the other one which is a little bit more tractable, and try to convince you that they are related and that the relation might be a good way to address the first one. So the main object, the main motivation for what I'm going to talk about is called the once reinforced random walk. I call it the one reinforced random walk. So if you want, it's the easiest model of self-interacting random walk that you can define. And let's work on Z2. So the model is defined like this. You fix the parameter epsilon, which is somewhere strictly between 0 and 1. And you want to define a random walk. And of course, there are several variants. You can do it in discrete or continuous times. You can do the self-interaction on the edges or on the vertices. And for instance, let's look at the vertex once reinforced. I will reinforce it on vertices. So the model will be the following. There will be, for every time, there will be a set AT, which is the set of visited vertices. So it's the set of all the XTs, of all the XS for S up to time t. So it will be some connected set containing the origin where you start. And let's draw it somewhere like this. And there will be a location of the particle, which will be xt, which is a point on the lattice. So typically, let's say that xt is here. And what you want to do is define a random walk which is affected by what it has done before. So what you do is, if one of your neighbors has been visited before, so for instance this guy, you will jump to it with rate 1. And if you have a neighbor which has not been visited before, so this guy, which is a new site, well, you jump to it with rate epsilon. And that's it. That's the process. Once you visit a new site, you add it to AT. And so the pair, like this here, is a Markov process with values in pairs of one set and 1 point in this set. So it's a very easy process. It's a self-interacting random walk. And all the natural questions on random walks can be asked about this process, and essentially all of them are open. So the main question is whether this random walk is recurrent or transient. So is the process recurrent or transient? And of course, you want to say that you start on Z2 where the walk is recurrent. What you do is a reinforcement, but it can be seen as a walk in conductances which evolve in time. But at every time, if you freeze the conductances, what you see is some lattice with conductances, and this lattice is recurrent. So you want to say that the walk has to be recurrent, and it should be an easy thing to prove. But then when you start thinking about it, it's well, if it's open, it's because it's not that obvious, and it's possible to build evolving conductances that will be recurrent at every time, but still will make the walk, say, drift to plus infinity in one particular direction. Typically, if you increase the conductance to the right of the walk, then, well, it's still a recurrent graph, but you can give the walk a drift. But nevertheless, the conjecture is that if you take something which is recurrent and you want it to spend more time where it has been before, well, it will want to make it go back to 0 more often than a simple random walk, so it's a natural conjecture that it's recurrent. And so here's the claim that I want to state, and I cannot prove, but I want to try to convince you that it's a reasonable claim. So the claim is the following. So there is some K which is a compact set, which is convex, which has non-zero interior. So the claim will be a shape theorem with this shape, so such that if you look at the location of the walk at time t, so you look at xt, and you normalize this by t to the minus 1/3, then this converges in distribution to the uniform distribution on the set K. So that's the claim, that there would be a shape theorem for the set AT. So the corresponding statement on AT would be that this would converge in probability for the Hausdorff metric, as usual for the shape theorems, to the set K. So the statement is, if you look at the once reinforced random walk for a long time, the set of visited vertices will tend to have a deterministic shape, and that it will grow at the speed t to the 1/3.
Does this K depend on the size?
And this K, probably. But so I assume that epsilon is very small. So that's the claim, and morally this claim would imply recurrence because the growth of the volume here is less than time. So if you are kept in something that is sublinear in volume, well, this forces you to come back to the origin. So that's the claim, and I want to try to convince you that at least it's a reasonable claim. But I'm not saying that I can prove it, because you will see exactly, or more or less exactly, what is missing. So what is the reasoning about this claim? So the main thing that you might want to try is, well, start with an easier case, which is the case that is most strongly reinforced. So assume for the moment that epsilon is very close to 1, is very small, is very close to 0, is very small. So it means that discovering a new site is much less likely than staying in your past. So it's very strongly reinforced. And assume as well that t is much smaller than something like epsilon to the minus some positive exponent. So we look at the process for a slice of time which is not too large, measured in terms of epsilon. So what happens is, so the rate at which you discover new vertices, it's at most something like epsilon times 4 times the degree of the lattice. So certainly the volume of AT will be less than epsilon t. This is always true. It's not deep, and it's true. And what I mean by that is that you will take t small enough that the mixing time of AT should be much smaller than something like 1 over epsilon. So what happens if you do that? Well, you have this set AT, which is somewhere here at a given time, which is less than this, or it satisfies this condition. So what the process does is it will walk inside AT. Essentially, it will be reflected on the boundary, because this is very difficult to do. And it will equilibrate before it has a chance of seeing that it's actually possible to discover a new vertex, because epsilon is very small. So what happens is that, so xt will mix in A, so in the current explored set, before discovering the next vertex. So before adding a new vertex. Okay, so what will happen is that you will have a walk here which is reflected in AT. It has some invariant distribution as a reflected random walk, and sometimes it will be on the boundary, so it will have this invariant measure will have a trace on the boundary. And the only times where you can add a vertex to A will be times where you are on the boundary, and when you are on the boundary, with rate epsilon, you will add new sites. So essentially, the way you will add new vertices, so the law of the next site added to A is the same as the trace on the boundary. So well, you need to look exactly. This will depend on whether you reinforce by edge or vertices, but the gist of the idea is that the law of the next site added to A will be essentially the same as the trace on the boundary of A of the invariant measure of the reflected random walk in A. Okay, so you mix, you are at invariant measure. Sometimes you visit the boundary, sometimes you don't visit the boundary, and when you are on the boundary with rate, which is epsilon, you add a new vertex. And this is completely clean. As long as you have this inequality, that the mixing time is less than any possible time between adding successive vertices to A, this is true. So just one remark, inside A, what you have is simply a simple random walk in some graph in continuous time. So the invariant measure is completely explicit. It's the uniform measure in the set A. And so the trace of this on the boundary is just, it's essentially the arc length on the boundary. And the only place you need to be a little bit careful, and the only place why this is not an equality, is just that, say, if you have a corner on the boundary like this, the rate at which you will add this vertex is just twice what it would be if it was flat, because you can add it from the left or from the bottom. So it's something local but bounded, and it's still completely explicit. So if you focus on this model, this defines a growth process, which was actually mentioned this morning in Chris Bird's talk. This is up to this counting of number of neighbors, which doesn't essentially change anything. This is the same as the even model. Essentially, you add a point out of all the neighbors of A, and you all add them with a rate which is essentially the same. And the even model, it has a shape theorem. So as long as you have this condition star here, so as long as this condition star holds, what you have is that the way A grows is the same as the way the Eden model grows. So AT is the same in distribution, up to slight error terms depending on what exactly you put in star, is the same as the Eden model at some time which measures the local time that the walk spends on the boundary. So at some time. And so in particular, because the Eden model has a shape theorem, you know that AT will essentially be some rescaling of the deterministic shape that the Eden model takes. And so it will really be something that is smooth and deterministic up to the size. And that's why the claim is this, that K would be the asymptotic shape of the hidden model. And the law of the walk inside this shape is just the invariance measure for the reflected random walk, which is the uniform measure in K.
But you've got the restriction T much less than epsilon.
Of course, which is, I'm not claiming that this is true for all times and that this is a proof of this shape theorem. I'm just saying that this is step 0 of the proof. But step 0 is fine. Notice that I didn't claim that K was the same as this shape. I said that it was reasonable to expect that there was a shape and that at least for small times the shape is this one. Okay, I still need to explain this exponent 1/3 here. So here, assuming that there is a shape, you can just do dimensional analysis. So let's call Vt the volume of AT and RT to be the diameter of AT. So because there is a shape, Vt behaves like RT to the square. And the size of the boundary is also proportional to RT. This is still, it's dimensional analysis. It's not true at the microscopic level, but it's just a way to predict this exponent 1/3. And as we saw this morning, it's actually true at infinitely many times, and that, well, you can make that into a proof. So what happens is that if you look at d over dt of Vt, so the speed at which you add vertices to the shape, well, what is it? If you want to add a vertex to the shape, you need to be on the boundary. And the proportion of time you spend on the boundary is the relative volume of the boundary compared to the volume of the set. And when you are on the boundary, you add a new vertex with a rate which is this epsilon here. So you have this epsilon. And then you do that, you plug RT inside, so you write Vt is RT squared, this is RT, this is RT squared. You solve the equation, and what you get is that RT should scale like epsilon t to the power 1. And the volume should grow like epsilon t to the 2. So this is doing as if everything was deterministic, but since you are at equilibrium at all times, it's not difficult to turn that into a proof that as long as this condition star is satisfied, the speed of growth actually is t to the 1 with this factor epsilon in front. Okay, and just one remark. If you did that in higher dimension, what you would find is that this step 0 is still correct. It's still true that you are looking like at the reflected random walk in the current shape. And solving this, you would get that, so in ZP, what you get is that RT scales like epsilon t to the 1 over d plus 1. Yes?
When you say that RT, the boundary has length RT, sort of in the discrete sort of, I mean, are you using something about the smoothness of discrete Eden or something? I mean,
yeah, not really. I mean, if the boundary is too thick, you will add vertices, but they won't change the actual diameter. So you can make that. You can argue like that. Or you can use the Damron result that was mentioned this morning, that at infinitely many times you actually have something like square root of the volume. And you look at what happens between these times. And then it grows like exactly like this. Okay, so this is safe, and it is a justification of the claim, at least for small times. But of course, it's not a proof, because everything will break down if you wait longer, because you don't have that, and then it becomes something complicated. You don't have the time to mix before you add new vertices, and everything breaks. So what do you do? That is step 2. So this was step 1 for small times. Step 2 is you want to do some kind of coarse graining and show that estimates like this, statements that you have a deterministic shape, an explicit speed, and something like that, and smoothness of the boundary, propagate from one scale to the next and get better from one scale to the next. And if they do, well, it will be a little bit more convincing that this claim is true. But as you know, if you have read papers with coarse graining and renormalization, going from the intuition to the proof is what is difficult, and this is what we don't know how to do. But at least this step still is convincing, I think, to me. So let's do something like this. Take L, which is a rescaling parameter, which is something large, but it's still small enough that at this scale L, this assumption is still satisfied. So the mixing time of anything that is smaller than L is still much less than 1 over epsilon. And so what you do is you slice your lattice, Z2. So Z2 is somewhere here, and these are blocks of size L. So at least at the beginning, the shape will be smooth, and you choose L, which is small enough that it will still be smooth at the scale at which you discover many squares. So the actual shape will be something like that. And it will have, well, the squares will be classified in 3 kinds of squares. There will be completely visited squares, which are deep inside A, and in which the random walk is just doing the simple random walk path. There will be unexplored sides here outside, which, well, are not on the path yet, so you don't see them. And along the boundary, there will be some layer of thickness 1, because for now we are assuming that the shape is smooth. There will be some layer of thickness 1 of partially visited squares.
They can be also inside, no?
Sorry?
They can also be inside the not visited square.
They can be
Inside the shape.
Yeah, there can be holes. Yes.
But this we are not counting. Like,
I can draw a hole like this if you want and state that this is partially visited. But part of the statement that the Eden model has a shape theorem is also that it doesn't have holes away from the boundary. So this is very unlikely to happen deep inside the shape, if you assume that this is the right behavior. So at least heuristically what happens is the same as at scale 0. You have some shape with a boundary, and you have a walk that is reflected inside. It does a simple random walk inside when it's far from the boundary. When it is on the boundary, it discovers new sites. And when it's done exploring this square, only then it's allowed to access the next square. So at this level of detail, which is not a very huge level of detail, it looks like it should behave at this scale like, again, like a once reinforced random walk. You go from square to square like a random walk inside the current shape. You try to break the boundary a few times. And this is what happens here. You will try to go from here to here. And after 1 over epsilon tries, you will be able to jump. And this is the same. You will visit this square a few times before you discover enough that you can access the next one. And essentially, if there is a scaling argument, it will look like that. It will say that at the block level, the process will still be something like a once reinforced random walk, maybe with a different parameter. And so if you do again the dimensional analysis, well, you will define a rescaled coordinate which will be x over L. So this is just a number of blocks as a function of the microscopic coordinate. You will have to do a time change. And the time change is natural. It's given by the diffusive scaling of the Brownian motion or the random walk inside the domain. The time you need to go from one block to the next is scaling like L squared. So this should behave like T over L squared. And, well, the radius is scaling like 1 over L. So you have these two parameters, you plug them into the equation that we had here, that the radius should be epsilon t to the 1/3. And if you solve, what you get is that the new reinforcement parameter, the epsilon tilde, if it is indeed the right model for what happens at this scale, well, it's given by matching the growth speed in any range at which both descriptions should hold. And if you do that, it just amounts to replacing r and t by their rescaled parameters. And what you get is this. That's the new reinforcement parameter is itself scaled by a factor which depends on L, but it's made very small. So that's exactly what you want if you want to implement some renormalization scheme. You want one renormalization which is some kind of coarse graining like that, and you want the small parameter to become much smaller. And this is what happens. So this is, on this model, this is what we have. That there is a natural rescaling argument that predicts that it should grow like t to the 1/3 with epsilon in front of the t, and that there should be some deterministic shape. But here already the shape is not the same as for the initial Eden model, because there is no reason that the microscopic details would give the same shape. So of course this is not a formal proof, because if you want to implement it, you need to actually control that the layer on the boundary has thickness 1, that if you have discovered enough of a square, it is like if it was completely discovered, and that you can jump through it without paying any additional price. But essentially, it will be turnable into a proof if you have enough geometric control of the boundary that itself propagates from one scale to the next. And this is what we don't have on this process. But it's something that actually you can do on some other model, which is closer to internal DLA and which is well, easier to study as a process because it's simpler. So let me describe this process, which I like a good name for this process, so if anybody has a suggestion, it would be very nice. I want to call it bouncy IDLA. So here is the process. The process is defined as this. You start with a map phi, which goes from Z2 to Z2. And if you've seen talks on excited random walks, this is the cookie profile. So this is, on each site, you have one instruction which is a cookie, which you will use the first time you visit a vertex, and then the vertex becomes normal. And so what you do is, you have Z2, you start at the origin, you do a random walk, so xt, xn, will be a simple random walk, except that at the first visit of a vertex, if you jump onto a vertex that has never been visited before, so at first visit, you replace xn by xn plus phi of xn. So the first time you visit a vertex, you find the cookie, you eat the cookie, and it makes you jump to a new location, and the size of the jump is given by phi. So just a few trivial examples. So if phi of x is identically equal to 0, then there is no cookie, and this is a simple random walk. And you find the internal DLA by setting phi of x to be exactly minus x, which means whenever you discover a new vertex, it tells you to jump by minus x, so it tells you to jump back to the origin. So this is exactly the same as the IDLA. And the main point is that if you want to make a model of the once reinforced random walk, if you want to make that fit in this model, what you want to do is make a cookie of a different nature which tells you that you need to back off, to backtrack your last step. And if you do that, essentially what you get is the once reinforced random walk with epsilon equals to 1/2. So it doesn't fit here because it would need to see the way you arrive at the site to discover what it is telling you to do. And that's what you gain by adding something like that. You fix phi in advance, and it perturbs the random walk, but in a way that is more independent of the random walk. So hopefully it's easier to study. And nevertheless, if you remember the motivation here, you had this shape and you had this random walk which was reflected on the boundary. Essentially, it should still look the same as what you get if you take phi to be something that tells you to jump towards the origin. Essentially, that's the model that will look like what we want as a scaling limit for the once reinforced random walk. So the bouncy IDLA will be what you get by setting phi of x to be minus x over the norm of x to some power 1 minus a. So you fix an exponent a between 0 and 1, and when you are here, you jump towards the origin by some jump of size norm of x to the power a. And so a is equal to 0 is the simple random walk, a equal to 1 is the IDLA, and a in between, it should kind of look like once reinforced random walk, and it should be something interesting. So I don't know how to find a better name than bouncy IDLA. It's not exactly IDLA.
So what you wrote as a
Claim. A claim is not a theorem.
No, a claim is a claim. It's a statement. It might be wrong. There are wrong claims.
We tend to use the word conjecture for that.
It's not a conjecture.
It's not a conjecture.
It doesn't have the status of conjecture yet. It has some support, but not enough to be really a conjecture.
You can call it conjecture. You don't yell that much to make it a conjecture.
I think it's true. And it fits the simulations. I made simulations. I don't want to show them to you because the simulations are just one disk in the middle of a slide. So
Looks like a conjecture. Sounds like a conjecture.
okay, it's a conjecture. So here's in 5 minutes some interlude, which is something not difficult, but it's nice if you want to explain to your students what adapted is and what a random walk is and what it means to be recurrent. So it's a game on Z. So the game has 2 participants. So participant number 1 is a random walk. And the random walk is just a sequence epsilon n of IID jumps, which are nearest neighbor jumps. And the second player is a daemon. And what the daemon is allowed to do is at time n, it looks at the random walk where it is at time n, and it gives the random walk a push or not. It just teleports it anywhere on the plane. So it can move the random walk elsewhere. And so the goal of the random walk is to be recurrent. So the random walk wants to come back to 0 infinitely many times. And the goal of the daemon is to make the random walk transient. So this is a stupid game if there is no restriction on what the daemon can do, because you can just push the walk to the right, and then it will be transient to the right. And the second thing is I didn't say that the daemon had to be adapted to the filtration generated by epsilon n. So there are 2 features for the daemon. So the daemon can be adapted or not. And adapted means that it decides where it pushes the random walk, seeing only what the walk has done before. It has access to all the epsilon n, not only the location. So it's slightly more general than this. But it cannot see the future. And the daemon can be here as well. I need a word to say that. So far I'm calling that nostalgic. And nostalgic means that it can only push the walk towards the origin. So it wants to make the walk transient, but it still remembers that, well, walk is belongs at 0. So it wants to not cheat and not reveal itself, and by that it wants to push the walk towards 0. And the question is, can the daemon win if it is adapted, if it's not adapted, if it's not nostalgic or not? So certainly this is necessary for the game not to be trivial, because if you are allowed to push the walk away, well, it's easy to win, you just push the walk away. So what if the daemon is adapted? Then it should be easy, and in fact it is. It's just a 2-line martingale argument that tells you that if you are adapted unnostalgic, then the walk has to be recurrent. And you can make it even a little bit easier by saying that by nostalgic you mean that if you look at the green function of the random walk, you are only able to push the walk to a site where the green function is smaller. Then it tells you that the value of the green function at the location of the process becomes a super martingale, so it has to come back to 0. So it's an easy, essentially 1-line martingale argument. So just to tell you, this is essentially what the difficulty lies if you want to implement something like that for the once reinforced random walk, is that you are not nostalgic, but you want to have something still local. So when it becomes a little bit more fun and you can use it with your students, this is really just the definition of the green function. So what happens if it's non-adaptive? But still you are only able to move the walk closer to the origin. So the condition is that xn is moved by the daemon to x prime n such that x prime n is less or equal than x. But the daemon can see the future. It can see what the walk wants to do. So what happens? Well, let's start with the easy case in dimension 1. What do you think? In dimension 1, can you make the daemon win, or? So in dimension 1, you can have an easy coupling argument. If the walk is here, and you're only able to push it closer to 0, so between 0 and the current location, well, this is the initial random walk. You will push it down sometimes. Well, just by coupling, it will have to touch 0 before the initial walk. So it seems that the daemon cannot win. But I'm cheating a little bit, because this condition is not that you send it closer to between 0 and xn, you send it closer to 0. And if you want to use technicalities to win, which is allowed, well, you can win by saying that you look at the path of the simple random walk, you look at the successive record breakings, like this, and negative record breakings. And what you do is, when you are here, the daemon knows that you are here because it can see the future, and what you do is you push the walk down to -1, which is closer to the origin. But then the walk will still walk away, and then you push it up and it will still walk away. And if you push it a little bit further away, say half of this on the other side, well, you can ensure that the perturbed walk will be transient and go to infinity in norm. So this was kind of trivial. In 2D, this is what you want to do. You want to do something that looks at the future of the walk and pushes the walk in such a way that you push it towards the origin in such a way that 0 is not in the path anymore. And you can do it like this, by doing that in one coordinate and nothing in the other coordinate, and it works. You can do something a little bit nicer with a bound on the number, on the size of the pushes that you are allowed to do. And this is what I mentioned yesterday to you, yesterday evening. What you want to do is you fix a sequence of radii. This is 2 to the n, this is 2 to the n plus 1. If the walk is here, and you are the daemon, what you do is you look at the path until it touches radius 2 to the n plus 1. And you look at whether this contains the whole interval here between 0 and some distance in the direction of where you are. And if this is not covered, if there is a point here which is not on the path, well, you just push in such a way that this is shifted to the origin. And so it's a small push. Essentially, you need something like log of the radius to find a point that is not on the path. So by a small push towards the origin of small size, you can make the walk transient. So proving that you can do it like that, it requires something about the cover times of balls and intervals. If you just want to show that you can do it with a shift that is, say, less than 1/2 here, it's just, you can just do a Borel-Cantellier argument. So the point of this was that if you want to show that the bound CI DLA or a process like this is recurrent, well, if phi is pointing to the origin, it has to be recurrent by this martingale argument. If it's not, for instance, if it's a once reinforced random walk, this is telling you that, well, there is no free one-line argument because there are cases where it's actually not recurrent. Okay, so what can we say about this process? So here's a claim, and that's a better claim. This is, I'm writing it down and I know essentially all the steps, but so I'm much more confident in this claim. And the claim is that the bouncy IDLA with A between 0 and 1 has an asymptotic shape, which is the Euclidean ball of appropriate scaling in the volume. So if you do that and you point towards the origin, if you push enough, then the shape is the Euclidean ball. So let me give you some flavor of the proof and then see what I have time to say. But I want to finish early because that's the tradition of the last speaker of each day in this conference. I don't want to overflow the time I have. So how would you prove something like that in dimension 1? So the proof in one dimension. So in one dimension, I don't mean on the line, because on the line the process is kind of trivial. But let's say you are working on a strip. Okay, so you want to show that on this strip you can control the whole geometry of the process in such a way that you get a good control on the asymptotic shape. So this is the width of the shape. So at any given time what you have is some boundary between a visited set, which is this, so this is visited, and this is not visited. And think that this is the location and 0 is far away. So you want to have control on the fluctuations of this part of the interface under the assumption that the jump here, so the amount that you jump whenever you discover a new vertex, is going to infinity fast enough. So just I will do a simulation. you arrive here, you add this vertex, and you jump here. And then you start again, you walk, and you will discover this site, and then you jump somewhere. And that's what you do. So here the key point is that you know IDLA. You want to use IDLA instead of doing all the complicated things that, if you're not Gregorian, you cannot do the complicated things that you need. So you want to use IDLA to say something. So you want to say that essentially the way that this will evolve is essentially the same as with IDLA. It's essentially the same as if you jumped all the way back to 0. And it is as soon as you can control that this distance here between the closest unexplored point and the image of the furthest one by the jump is large enough. And essentially, if this is larger than L, it means that the harmonic measure from here and from 0 on the boundary here is, well, it's absolutely continuous with each other. So you can do it by hand if you want. You can say that the harmonic measure of this guy here is something that is at least some constant over L. This is the lowest take argument about harmonic measure. It's really the bound that you get just the first time you think about it. The harmonic measure of this here, while it's smaller than, so what's a good scenario if you want to touch something here? Well, you need to arrive here before touching this guy, and it's less than C over L divided by log L, by log of the, let's call this delta T. Delta T. Just by saying that the walk is recurrent, so if you are here and you want to reach here before touching this, well, the probability of this goes to 0. So if you look at the width of delta T, this point goes to the right with this rate, this point goes to the right with this rate, which is much smaller. So as long as you are sure that the walk jumps to the left with each cookie, this is true, and you can propagate this. So what you get is that as long as phi of x is bigger than delta t, so as long as the jump takes you out of the shape, then delta t is controlled by a burst and death process, which is recurrent to 0. And this gives you a control on the fluctuation. And so if, well, whenever delta t becomes bigger than the current jump, this doesn't work anymore, but you just focus on this point, you forget about all the part of the boundary that you have here. You know that the walk is recurrent, so you know that this will be taken care of eventually by the walk, and you restart the argument as if you started from here. And this controlled by a burst and death process tells you that as long as this is true, delta t grows like log t. And if phi of x is large enough, like a power of the distance, then this will be true with positive probability for all time large enough. So you get this control for free, or for very little technology. So this is the argument in 1D, and this is what, so it works.
In this simple example, if phi was minus 1 million but fixed, what would happen?
Well, then you would find something like a simple random walk. It's not large enough to change the behavior of the system. You really want a jump that is large enough that you can mix whenever you come back.
But would you have fjords that?
Yeah, you would not have this nice control. You can still figure out what happens in one dimension, but so the cookie walk in one dimension, it's still, well, it's still growing diffusely. You don't have enough cookiness to make you more recurrent than you should be. So you really need an extra dimension transversally if you want the cookies to change your behavior. Okay, so if you wanted to do that in 2D, you would want to do the same. You would say that whenever you have a control on the fluctuations of the interface, And whenever you take phi, which grows larger than the fluctuations of the interface, then you could do that. And if you do that, it's it's a self-fulfilling prophecy somehow, that if you know that the interface doesn't fluctuate too much, you know that it's controlled by internal DLA, and internal DLA doesn't fluctuate too much. So essentially, as soon as phi of x grows quicker than the fluctuations of the interface of an internal DLA, you can couple the two processes. So you need to bootstrap the argument a little bit at the beginning, and that's why I'm not quite sure how to do that if you put a log here instead of a power. But certainly, if this is larger than r to the 1/3, then this would work. Okay, so yeah, I guess that's probably a good point to stop. Yeah.
You cannot really couple to internal DLA, can you? So there will be this exceptional things where you will see that it's not internal DLA. So how do you? I mean, I didn't quite get the end. I mean, in the 2D case, when you want to couple with, you're using Rivian and the coupling with the.
If you want, you can couple it with the internal DLA with uniform starting point. If you know that you are kind of uniform on the boundary, your image by phi is also uniform on the image of the boundary, and this is rotational invariant. So if you have something like this, if you mix fast enough, so if this is large enough, you mix fast enough to be comparable to the internal DLA. So that's why maybe it's not possible to go down as far as you want here. Maybe you need a rubber band on A. Okay, so as you see, this is kind of, well, it's work in progress, and maybe it will not work all the way, but so the idea would be that if you can compare these two processes, and if you can look at that and prove something using this kind of technology, well, the goal is that after a while it should maybe tell you something about the one-third force one. So I'm sorry that there is no theorem, but yeah, if you want, there's a theorem in dimension 1. But it's, yeah. So yeah, that's.
You did your talk backwards.
I did.
Talk was from IDLA to.
Yes, maybe I should have done it in the other direction, but but the motivation was not this. Okay, so I guess it's my job to close or start the closing of this conference. So, and I have to thank Stas for giving me this job, because it's not something I'm very comfortable doing. He would be much better than me. So I guess, first of all, we should thank Mike, essentially, for doing most of the chairing and most of the organization here locally, and Tom as well.
No, thank Mike.
But from the outside, essentially. And I guess we should thank Greg for making everything possible, right? For being there and being Greg. I think that. And I think Mike has